This is part 2 of getting ready for the second semester final exam. So this is a little redundant here, but we've got the extra practice with naming the compounds here. So let's see. First one, it's just sodium carbonate. So you have to recognize that CO3 is one of the polyatomic ions. Going down below it, same thing. You have to recognize that SO4 is a polyatomic ion. It's lithium sulfate. Now letter C is a little bit different because we've got a transition metal. So we're going to need to use Roman numerals. Hydroxide has a -1 charge, and there's 2 of them. So how do we cancel out a -2 charge? With a +2 charge. So that must mean that this compound is copper Roman numeral 2 hydroxide. There's more practice with polyatomic or with Roman numerals here. Each chlorine has a -1 charge, and there's 3 of them. So how do we cancel out a -3 charge? This would be iron Roman numeral 3, showing that it's a +3 charge, chlorine. In other words, this iron loses 3 electrons, and each electron fulfills a chlorine's outer shell. This one is just simple. We don't need Roman numerals because potassium is not a transition metal. So this would be potassium carbonate. You have to recognize CO3 like in 11A. And 11F, you need to recognize that NO3's name is nitrate. Again, those will be on your solubility table. On the left-hand side, it names all of the polyatomic ions, so you don't need to have those memorized. Alright, we're into drawing things and naming the shapes. And is it polar or nonpolar? So let's do a little review. Let's do a review of all the different possibilities for shapes. If you've got 2 atoms or 3 atoms and they're all in a straight line, that's linear. If you've got 3 atoms and there are lone pairs, or at least one lone pair on the central atom's the one in the middle, then it has a bent shape. So a lot of people get confused because something might be drawn like A, and maybe you've got B here, and people will say, oh, this is linear. But no, it is bent because there are lone pairs on the central atom. Doesn't matter how you draw it, it's what is it actually in 3D. Okay, besides those, there's also pyramidal. That's when you've got 4 atoms, so there are 3 atoms on the central atom, and there's a lone pair on it pushing those 3 things down. That's pyramidal. An example would be like NH3. Then we've also got trigonal planar. This is when there's no lone pair on the central atom. Nothing pushing those 3 things down. So trigonal planar. An example of this would be like CH2O. That carbon has no lone pairs, so that is all in the same plane. And then the last shape, when you've got 5 atoms, 4 attached to the central atom, trying to draw it in 3D, that's tetrahedral. Now, a big question I always get is, how do you tell if something's polar or if it's nonpolar? Well, let's refresh your memory of what polar even means. Polar means that the molecule has 2 sides, 2 poles. One side is partially positive, one side is partially negative. So you need to use your electronegativity chart because that tells you which atoms are the greedy atoms. So I'm going to turn to that just to show you what it looks like again. And then you'll need to take this out while you follow along. So remember, the most electronegative atom is fluorine. Okay, 3.98 on the scale. The least are the noble gases because they don't form any bonds, so how could they be greedy within a bond? They don't fit in by definition. Okay, so we've got all the nonmetals to the right of this zigzag, plus hydrogen is over here, even though it's an exception. these things, the only nonmetals can form covalent bonds. So when you're talking about polar or nonpolar, that means you're only dealing with these atoms here. Sorry, not the noble gases. I didn't mean to circle them. Okay, so how do you tell if something's polar? If the difference in electronegativity between two atoms is greater than 0.5, let's see, so let's make a little chart here. If something is polar, that means the atoms have a difference greater than 0.5. They're all nonmetals. And something is winning. And what I mean by that is something is pulling and creating these partial charges. I'm going to give myself a little bit more room here. Okay, so let's look at an example. So for example, if you have HF, the difference is greater than 0.5. This is 2.1 on the chart. This is 3.98. You always draw an arrow pointing at the greedier atom, the one with the bigger number. That means fluorine is stealing part of hydrogen's electron cloud, creating this partial negative charge. Hydrogen's got this partial positive charge because it's got a lack of electron cloud around it. Things that are nonpolar, nothing is winning. So that can mean a couple of different things. It can mean that poles cancel out, or it can mean that you're talking about it's a tie. You've got two of the same atom. So for example, F2 would be nonpolar because nothing is winning here. They both have an electronegativity of 3.98. Or something like carbon dioxide, CO2. This oxygen is pulling to the right. This oxygen is pulling to the left. So sometimes you have to know how to draw its shape to tell if it's polar or nonpolar. Another example of something that's nonpolar would be CF4. You've got a tetrahedral shape. One's pulling up, one's pulling towards the bottom, one's pulling towards the right, one's pulling towards the left. So everything cancels out. That would be another nonpolar. Okay, so let's go back to the original question here. It says it would like you to draw C4H10O and C2H4. Okay, so I'm going to give myself a little bit of room here so we can draw these two and try to name their shapes. And it also wants us to tell it if it's polar or nonpolar. Okay, I think we've got enough space here. C4H10O. So remember honk 1, 2, 3, 4. Every carbon needs to be surrounded by 4 things. Oxygens, it's 2. Hydrogens, it's 1. So C4H10O. See if we've got 10 H's here. We're looking pretty good. And I'm going to draw the lone pairs on the oxygen. So what shape is around each carbon? Each of these carbons, all 4 of them, have 4 things around them. Okay, there's only one shape that can be. That's tetrahedral. So all 4 of these have a tetrahedral shape. There's only one other central atom. Central atoms have to have at least 2 other atoms attached to it. That's this oxygen. Now there's 2 things attached and I drew it in a linear shape, but you know better. Since it has those 2 lone pairs, it has a bent shape. Is the molecule polar or nonpolar? So if this is truly bent, I'm going to redraw this. So this is all the C's going down here, and this is the H. This oxygen is much more electronegative than the carbon and the hydrogen. So it's pulling. and it's creating a partial negative charge. That means that, yes, indeed, this molecule is polar. So C4H10O is polar. Okay, how about C2H4? Let's draw it out. C2, I'm going to draw it using the Lewis dot structures in case you need a little review. Each of those carbons has 4 dots, so I'm going to bond them at least once. And then we've got 2 hydrogens on each side. Try to make things symmetrical. Okay, and now we can connect these one more time. So if I were redrawing this nice and neat, I would have a carbon with the double bonds surrounded by these hydrogens. Okay, first, what's the shape around each? Well, each of these 2 carbons has 3 things around it and no lone pairs. That means the shape is trigonal planar. They're all in the same plane because there's no lone pair. How about the polarity? Is that polar or nonpolar? Nothing's winning. Carbon and hydrogen do not have a difference greater than 0.5. Therefore, this molecule is nonpolar. Okay, let's get a little bit more practice with 13 and 14 here. 13, it says draw PF3. P has 5 valence electrons and each F has 7. So you can see nicely how these 3 fluorines are going to bond with the phosphorus. Okay, and what's the shape? There's 3 things attached and there's a lone pair. That means that this is going to be pyramidal. Is it polar or nonpolar? Well, if you picture this as a little pyramid and you look up the electronegativities, each of these fluorines is pulling really hard on that phosphorus. So each of these is going to have a partial negative charge, leaving that phosphorus with a partial positive. So this is definitely a polar molecule. How about the one below it, F2O? O has 6 valence electrons. Fluorine again, we just did one with it. We know it's got 7. So what shape is this? It's got 2 things attached and 2 lone pairs. This is bent. How about the polarity? Fluorine is winning. It's pulling by more than 0.5. That means it is very polar. 15, what type of bond would form? Well, sodium's a metal and oxygen's a nonmetal. So automatically, without even thinking, that's an ionic bond. How about if it's a tie? Oxygen and oxygen. That would be nonpolar covalent. Covalent because it's all nonmetals. And then P and O, you have to look it up, but they do have a difference greater than 0.5, so this would be polar covalent. Switching gears completely, number 16, what's the molar mass of each of these compounds? So as a little review, if you want to figure out the molar mass of something, you have to look at each atom's individual molar mass. Carbon's number 6, and its molar mass, 1 mole of carbon atoms weighs 12.011. Okay, hydrogen's number 1, 1.01. Oxygen is number 8, mass 16. So C6, we've got to do 6 times 12.01, 0.011, plus 12 times 1.01, plus the 6 oxygens, 6 times 16. Add all of that together and it adds to 180.18 approximately grams per 1 mole. So what that's saying is if you've got 6.02 times 10 to the 23rd of this molecule, on the scale it's going to weigh 180.18 grams. How about a little bit more of a complicated one? We've got NH4 Some people like to see it drawn out. It kind of helps them figure out how many atoms are there. And then one more nitrogen. So we've got 1, 2, 3, 4 total nitrogens, and we've got 4, 8, 12 hydrogens. So we've got to do 4 times 14.01 plus 12 times 1.01, and that adds to 68.16 grams per mole. Okay, now we got to use a molar mass. So number 17 says, what if you've got a fraction of a mole? You don't even have 1 mole of calcium phosphate. Well, first we got to figure out how much does 1 mole weigh. We've got 3 calciums, so that's 3 times 40.08. That's calcium's molar mass on the periodic table. Plus, we've got 2 phosphoruses, because there's 2 PO4s. So 2 times 30.97 plus 2 sets of 4 oxygens, that makes 8 oxygens, 8 times 16. So if we had 1 mole of this stuff, it would weigh 310.18 grams. But we do not have 1 mole. We have 0.658 moles of Ca3PO42. Okay, so we got to set this up. If we had 1 mole of Ca3PO42, it would weigh, this is like a big equal sign, 310.18 grams. I'm going to draw a line here. How do we solve this? Multiply everything on the top, divide by the bottom. So 0.658 times the 310.18 comes out to be 204.1 grams of Ca3PO42. All right, number 18. What's the strongest intermolecular force acting on the molecules? So there's a great way to figure out what the strongest intermolecular force is. First, you ask yourself, is the molecule you're dealing with polar? And the easiest is when it's nonpolar. If it's nonpolar, it has dispersion forces. These are the weakest. That means that these molecules don't really care about each other. There's only a weak interaction between each other. So, for example, I'm just going to skip down to CO2 here. I'm going to draw it out. Here is a carbon dioxide molecule. You can see, because those poles cancel out, that this is nonpolar. So it's going to have a slight attraction to another carbon dioxide molecule, but this is an easily broken intermolecular force. And that makes sense because carbon dioxide is a gas. They fly away from each other. They don't really care about each other. On the other hand, if your molecule's polar, you have to ask yourself another question. Does it have an H bonded directly to an F, an O, or an N? I always joke, chemistry is fun. That's how you can remember it. If it does not, then it has the middle forces called dipole-dipole. We'll see an example of that in a second. If it does have a hydrogen directly bonded to a fluorine, an oxygen, or a nitrogen, it has the strongest intermolecular forces. They're called hydrogen bonding forces. These molecules love each other, and they are very hard to separate. Okay, so let's look at examples. So we already said that carbon dioxide has dispersion forces between the molecules as their strongest intermolecular forces. How about CH4O? Well, let's draw it out. CH4, if I'm going to fit this O in here, I'm going to draw it in its correct shape. Okay, we've got it here. So first, is this polar? Well, the oxygen is much more electronegative than the carbon and the hydrogen, so it's going to have a partial negative charge. It's pulling on their electron clouds, leaving these partially positive. Since it has those two different ends, this is definitely polar. So going by your flow chart, you have to ask yourself the second question. Does it have an H directly bonded to an F, an O, or an N? Yes, it does. So these molecules have hydrogen bonding forces. What that means is this molecule with another molecule exactly like it, that bond is hard to break between them. I'm sorry, it's not a bond, it's a force. It's an attractive force. Okay, how about letter C? CH2O. This one tricks people because they automatically see the O next to the H and they say, oh, it's hydrogen bonding. Well, you got to be careful here. This is polar, but does it have an H directly bonded to an F, an O, or an N? No, it's bonded to a C. So that means the force present is dipole-dipole, that middle force. Finally, the last one, NF3, it's got a pyramidal shape, and each of these three fluorines is pulling down, down, down. So this is definitely polar, just like the last one was polar. But does it have an H bonded to an F, an O, or an N? It doesn't even have an H. So that means that this one also has dipole-dipole forces. And finally, the last question from this second page, which of the molecules would evaporate the fastest? Well, we already said this. The carbon dioxide molecules, because they have weak intermolecular forces between them. Easy to break. Which one would be the hardest? The one where the molecules love each other. CH4O. And that concludes page 2.